In this video, I'll highlight important concepts in sections 2 through 2.5 in your textbook. Our learning objectives for Chapter 2 are that students will understand the commonly used systems of units and the difference between fundamental and derived units. Students will be able to explain the difference between dimension and unit. You'll be able to balance chemical equations and apply stoichiometry to environmental applications. Students will also be able to define what is meant by oxidation and reduction, and you'll be able to develop half reactions. We will not emphasize the fundamental concepts of thermodynamics in this course. We also will not emphasize acid-base systems for determining pH and all chemical species involved at equilibrium. We will, however, make sure that you can comprehend the importance of the carbonate system and be able to calculate the alkalinity of a water sample. We will not emphasize solubility product calculations and their ramifications in this course. We will be able to use and apply the gas phase laws with special emphasis on Henry's law. And last but not least, students will be able to explain the difference between the three major groups of hydrocarbons and explain the major functional groups of organic compounds and their importance in environmental engineering. By way of introduction, I wish to emphasize that environmental engineers must have a firm foundation in chemical concepts utilized for treatment systems dealing with water, wastewater, residuals, and air pollution problems. Chemicals such as alum, lime, soda ash, and sodium hydroxide are routinely added to hard water to precipitate calcium and magnesium ions. Ferrous sulfate, ferric chloride, and lime may be added to wastewater to remove something like orthophosphate. Chlorine and ozone are often used for oxidizing organic compounds and as primary disinfectants in various environmental applications. Furthermore, gas laws are important since oxygen and nitrogen may be added to a reactor to enhance biological oxidation or to strip out unwanted gases. The chemistry and solubility of gases such as carbon dioxide, oxygen, and ammonia in water affect the rate at which they can be transferred into or out of solution. As engineers, we are not only concerned about the final or equilibrium concentrations that can be achieved during a chemical reaction, but, more importantly, the rate of reaction. 2.2 Dimensions, Units, and Conversions. Engineers work with measurements of physical quantities on a daily basis. The fundamental dimensions are generally considered to be length, mass, time, and temperature. Derived dimensions include velocity, which would be length over time, volume, which would be a length cubed, and density, which would be a mass over a length cubed. Students should be able to use SI prefixes as shown in Table 2.2 and be able to convert between various unit systems highlighted in Table 2.3. 2.2.1 Density. The density of a substance is defined as its mass per unit volume. In the SI system, the density of water is approximately 1,000 kilograms per cubic meter or 1 gram per cubic centimeter at a temperature of 4 degrees Celsius. And by the way, a cubic centimeter is a milliliter, which is important for converting things in the laboratory and whatnot. In the English engineering system, water has a density of 62.4 pounds per cubic foot at 39.2 degrees Fahrenheit. Table 2.4 lists densities for various substances that you might find of interest. 2.2.2 Specific gravity and 2.2.3 Concentrations. Specific gravity is dimensionless and is defined as the density of a substance divided by the density of water at 4 degrees Celsius, as shown in equation 2.2. The concentration of a substance in solution can be expressed as mass or weight per unit volume, mass or weight percentage, volume percent, moles per liter, mole fraction, and equivalents per liter. And concentration is clearly a derived dimension. The most widely used unit for concentration is milligrams per liter, which is equivalent to parts per million, or ppm, when the specific gravity of a solution is equal to 1. Dilute solutions are often expressed as micrograms per liter. 2.2.4 Mass volumetric flow rates. In environmental engineering, the flow rate may be expressed either on a mass basis, which would be called gravimetric, or a volumetric basis. The mass flow rate represents the quantity of mass flowing through a pipe or system per unit of time, as shown in equation 2.13. The mass flow rate of some component A in the volumetric flow is represented by equation 2.14. Please refer to these equations in your textbook. 2.2.5 Detention time. Detention time is defined as the average unit of time that a fluid particle remains in a system. Could be a reactor, a tank, or a pipe. Detention time is also known as retention time or residence time by environmental engineers. Mathematically, detention time is determined by dividing the volume of the tank or container by the volumetric flow rate, Q, as shown in equation 2.15 in your course text. 2.3 Balancing reactions. A chemical equation expresses what happens during a chemical reaction or chemical change. Environmental engineers use chemical equations for estimating the quantities of chemicals that are added to water, wastewater, sludge, contaminated gas streams, and the like. An equation is balanced when the law of conservation of mass is satisfied. In other words, the mass of all elements on both sides of the equation are the same and the net charge of all compounds is zero. A properly balanced equation represents the stoichiometry. It shows the relationship between the number of moles of each reactant and the number of moles of the various products. Please refer to Table 2.8 for the major steps in writing and balancing chemical equations. 2.4 Oxidation-reduction reactions. In oxidation reduction or redox reactions, atoms or ions undergo a change in their oxidation number, and this is always accompanied by a transfer of electrons. Oxidation is defined as a loss of electrons. Think Leo. Reduction is defined as a gain of electrons. Think Jer. Your friends Leo and Jer. Another way to remember is oil rig. Oxidation is loss, reduction is gain. If one element releases electrons, then another element must be present to accept the electrons. Furthermore, with these concepts in mind, an oxidizing agent is any substance that can add electrons. And any substance that can give up electrons is called a reducing agent. Refer to Table 2.9 for a list of common oxidizing and reducing agents. Here are the steps for balancing oxidation-reduction reactions. First, check to see whether any chemical species is being oxidized or reduced. Then, write and balance the half reactions. Then, fill in the remainder of the chemical equation. And lastly, check mass balance on both sides of the equation. There are examples of how to do this in your course text. 2.5 Thermodynamic equilibrium. Thermodynamics is the branch of science dealing with changes in energy that accompany physical and chemical processes. Thermodynamics allows environmental engineers and chemists to determine whether or not a chemical reaction will or will not occur. These concepts are very important, but will not be emphasized in this course.